Starship's re-entry glow reveals engineering reality. Those bright flashes weren't just spectacular. They expose critical V2 problems. Wide tile gaps let plasma leak through, overstressing coolant systems and threatening rapid reuse. How did SpaceX solve it? V3 tiles packed 25% tighter with ceramic nodes sealing every corner junction. These bonding points eliminate the triple-point leaks that plague V2 ships. Is this the heat shield breakthrough we've been waiting for? Let's dive right in. From late 2025 into 2026, Starship entered its most critical transition phase. Ships 37 and 38 delivered breakthrough data, but they also revealed something SpaceX couldn't ignore. During re-entry, heating spiked past 1,400 degrees Celsius on the windward side, and the V2 tiles started showing their limits. What exactly went wrong at those extreme temperatures? Two major failure points emerge. First, plasma found leak paths between tiles, pushing inward toward internal structures. Second, the coolant system beneath the tiles experienced dangerous pressure buildups where exposed metal met superheated flow. Those white streaks trailing across the hull weren't just discoloration. They were pressure blowouts. The coolant tubes were failing under stress they weren't designed to handle. Could tighter gaps alone fix this? When Ship 39 rolled toward Megabay 2, engineers immediately noticed something different. The tile surface looked unusually uniform compared to every previous vehicle. Independent analysts grabbed comparison photos and measured the gap spacing. It had shrunk by 20 to 25%. That might sound like a minor adjustment, but here's why it matters. Re-entry doesn't just attack the tile faces. Plasma actively hunts for weak points, and the gaps between tiles are exactly that. Every millimeter of spacing is an opportunity for superheated gas to penetrate deeper. How much heat can push through a gap that's a quarter smaller? SpaceX didn't stop at tightening spacing. They added something genuinely clever: ceramic bonding nodes placed precisely where three tiles meet. These aren't cosmetic fillers. They're high-temperature ceramics engineered to seal what engineers call triple-point leak paths. On V2 ships, those tiny triangular openings at tile corners were among the most vulnerable failure zones. Plasma would force its way through, overpressurizing the coolant lines beneath. By plugging these intersections completely, could V3 finally prevent the cascading failures that plagued earlier ships? But tile alignment reveals only part of the redesign. Footage of Ship 39 shows the tiles sitting noticeably flatter against the hull. That indicates SpaceX repositioned the mounting studs underneath. On V2, misaligned studs caused uneven tile elevation. Some protruded too high, creating turbulence, while others sat too low, forming pressure pockets. Both conditions accelerated tile damage during the most intense heating phases. V3's mounting system appears precision-machined, using new fixtures to guarantee uniform height across thousands of individual tiles. What happens when every tile sits at exactly the right elevation during a Mach 25 re-entry? The tiles themselves change too. While SpaceX hasn't confirmed the exact ceramic composition, the color and texture differences suggest improved thermal shock resistance. V2 tiles occasionally cracked not from peak heating, but from rapid temperature swings, expanding and contracting too quickly as the ship transitioned through different atmospheric layers. V3 tiles likely incorporate higher-grade silica or modified internal fiber structures that absorb thermal expansion more effectively. They may also feature a more flexible backing layer on the underside, addressing another V2 weakness where differential expansion between ceramic and metal sheared tiles off their mounts. Ship 39 represents another milestone. It's carrying what appears to be the first complete operational heat shield. Previous test vehicles left sections deliberately untiled around the chin and other areas for instrumentation access. That meant SpaceX never tested how a continuous, fully tiled surface performs under real conditions. Now they'll find out, because V3 faces far more demanding requirements than V2 ever did. Can a complete shield perform better than a partial one? Or does full coverage create new thermal management challenges? For true rapid reuse, SpaceX estimates only 2 to 5% of tiles can need replacement after each flight. That's airline-style operations. Land, inspect, refuel, launch again within days. V-2 ships lost dozens of tiles per mission, sometimes entire sections. Acceptable for a test program, but completely unrealistic for operational cadence. V-3 must prove it can take the punishment repeatedly. What tile loss percentage will Ship 39 actually achieve? Before flight, there's cryogenic testing. This isn't just pressurizing tanks, it's a torture test for tile adhesion. When Ship 39 loads liquid methane and liquid oxygen at minus 183 degrees Celsius, the stainless steel hull contracts. If tiles or adhesives can't handle that contraction without shearing loose, they'll fail during actual operations. Early V-2 cryo tests revealed several cold-induced bond failures. Engineers will monitor Ship 39 closely during tanking operations, looking for even slight tile movement. One loose tile during ground testing could mean dozens lost during flight. Will the new bonding system hold when the metal shrinks beneath it? Then comes Flight 12, Ship 39, atop booster 14 or 15. During re-entry, peak heating could exceed 1,500 degrees Celsius on the windward surface. Pressure distribution will reach levels several times higher than V-2 experienced because SpaceX plans a steeper descent profile. That's intentional. They're pushing the limits to see where V-3 breaks. If large shield sections fail, they'll redesign again. But if S-39's tiles hold up, it confirms V-3 is approaching the durability threshold needed for full reuse. How close is SpaceX to that breakthrough? The stakes here exceed anything Falcon 9's booster faced. Falcon 9 re-enters at roughly Mach 6 after a suborbital trajectory. Starship returns from orbit at Mach 25. The kinetic energy it must shed is approximately 25 times higher. That's why the tile system isn't just important, it's absolutely central to making the entire Starship program work economically. SpaceX has manufactured tiles since 2020, constantly refining production techniques. V-3 represents the maturation of that process, with reports suggesting manufacturing speed improved by 30%. But speed means nothing if the tiles don't survive. Is faster production creating better tiles, or just more tiles that need replacing? While SpaceX refines these upgrades, Boeing's situation with Starliner collapsed into one of aerospace's most expensive failures. NASA formally canceled all future crewed Starliner flights after the troubled crew flight test exposed hardware problems Boeing couldn't solve on any reasonable timeline. This wasn't a minor setback. It's a multi-billion-dollar disaster that started with what looked like advantages. Both SpaceX and Boeing won NASA commercial crew contracts in 2014. SpaceX got $2.6 billion. Boeing received $4.2 billion, nearly $1.6 billion more, because NASA believed Boeing would develop faster with fewer issues. Instead, Boeing fell years behind and burned through billions beyond the original award. As of mid-2025, Boeing absorbed over $1.5 billion in abnormal charges, with total losses likely exceeding $3 billion when combined with contract overruns. How did a company with decades of spaceflight experience lose so badly to a relative newcomer? The failures started with software. The first uncrewed test in 2019 suffered a mission timer malfunction that fired thrusters at wrong moments. A second software bug nearly caused catastrophic re-entry failure. Engineers caught it only hours before disaster. NASA later revealed Boeing skipped integrated end-to-end testing before flight, something considered absolutely mandatory in human spaceflight. The second uncrewed flight in 2022 reached ISS, but lost 4 thrusters and experienced cooling problems. NASA accepted it conditionally, warning the next flight needed to be flawless. Instead, it became the worst-case scenario. Astronauts Butch Wilmore and Suni Williams launched to ISS aboard Starliner in 2024, but thruster failures during approach made NASA question whether the capsule could safely return them. After weeks of debate, NASA made an unprecedented decision: bring them home on SpaceX's Crew Dragon instead. It's the first time in U.S. spaceflight history that astronauts launched on one spacecraft and were rescued by another. What does it say about Boeing's quality control when NASA doesn't trust the vehicle to bring its own crew home? SpaceX operates like an entirely different kind of company. While Boeing burned through billions chasing perfection and still failed, SpaceX iterated fast, learned from every failure, and kept pushing forward. That's exactly what V3 represents. The culmination of lessons learned from ships 37 and 38's weaknesses. The 25% tighter tile spacing, ceramic corner nodes, precision machine mounting systems, and improved thermal shock resistance, these aren't just incremental improvements. They're targeted solutions to specific problems SpaceX identified and documented during actual flight testing. Boeing talked about quality and heritage. SpaceX flew broken hardware, analyzed the data, and fixed it. Which approach actually works? Flight 12 will answer the biggest question: can V3 tiles survive repeated high-energy re-entries with minimal replacement? If Ship 39 lands with 95% of its tiles intact, we're watching the moment Starship transforms from experimental prototype to operational spacecraft. If it doesn't, SpaceX will redesign again, and they'll do it faster than Boeing could schedule a review meeting. The heat shield problem might finally be solved. But the only way to know is watching those tiles glow orange at 1,500 degrees Celsius during the next re-entry. What do you think? Will V3 tiles prove durable enough for rapid reuse? Drop your predictions in the comments below. If you want to stay ahead of every Starship development, hit that subscribe button for Space Update 24 hours and turn on notifications. Like and share this video if you're excited about what's coming next. Thanks for watching, and we'll see you in the next update.